to have 16 ounces of peanuts. The filling machine inevitably experiences fluctuations in filling, so a quality control manager randomly samples 12 jars of peanuts from the storage facility and measures their contents. She obtains the following data. Okay? The variation would change, particularly if they were like whole peanuts, right? Because some peanuts are a little bigger than others, and so you might end up with a little bit more than 16 ounces and maybe a little bit less than 16 ounces. So there's going to be a little bit of variability, but how much variability? So let's say we want to construct a confidence interval for the standard deviation of the population based on this sample. Okay, so we're given a sample. It says, verify the data are normally distributed by constructing a normal probability plot. Okay, we do that by putting all these values into list 1 and constructing a normal probability plot. Make sure that it does look like these values are coming from a normal distribution or an approximately normal distribution. Freedom is going to be equal to 11. And what is our sample mean and our sample standard deviations?
The mean is 15.89.
Standard deviation?
0.3492.
Okay. Make sure you're using S, not sigma. Right? Sigma is for the population, and this is the sample standard deviation.
Yeah.
Okay. So next it says, okay, so verify that the data come from an approximately normal distribution. So you have to do the normal probability plot. Once we do that and we see that they are approximately normal, then we know it does, or we're comfortable in saying that it does come from a normal distribution. Determine the sample standard deviation, we already did that. And now it says part C, construct a 90% confidence interval. Okay, so that means that we have to go over to our chi-squared distribution. Chi-squared distribution with degrees of freedom equal to 11. And we got to find the two numbers that trap the middle 90% of our data, which I like to call chi-squared left and chi-squared right. The left one and the right one. It's the one that trap the middle 90% of our data. So this area there is going to be 5%, and this area there is going to be 5%. So now we got to go to our table. Okay, so the first thing we have to go is down to 11 degrees of freedom. That's what we're working with here. And then we got to find the area to the right equal to 5. That's this one. So I get 19.675 for the right one. 19.675. And on the left one, I get 5, where did it go? 95. 4.575.
So it's 05 and 0.95, right?
What's that?
Like the areas?
Yeah, the area to the right is 5, and then the area to the right is 0.95. Okay, so we have those two values. And now, again, this part right here is not something you have to do, so I'm just going to put it one last time to do that formula. But instead of leaving it with all variables, I'm going to use these numbers. So let's say that in our sample, this would be some chi-squared value that comes from the formula n minus 1 times s squared over sigma squared, which we'd be happy to put in there if we knew sigma, which we don't. We don't know sigma. But we do know s. We know s from the sample standard deviation. So we're saying that between these two numbers, we're saying that between, let's use the black one, chi squared left and or equal is our chi squared from our sample, left and or equal to chi squared right. And now chi squared left, I'm just going to write it in as 4.575 is less than, and then this formula, which would be n minus 1 times s squared all over sigma squared less than chi squared right, which is 19.675. Right? There is a 90% chance that if I knew sigma, I would put it into this equation. There's a 90% chance that the chi squared value would land somewhere inside that region. Good? Okay, but we don't know sigma squared. That's what we want to identify. So I'm going to multiply everything by this to solve for chi squared, for sigma squared. So I'll end up with 4.575 divided by n minus 1 times s squared is less than 1 over sigma squared less than 19.675 divided by n minus 1 times sigma squared. Right? All I did is I multiplied everything by 1 over n minus 1 times s squared. So multiply all three parts of your inequality by that quantity. So here it just turns into that fraction. Here, the numerator and that denominator completely cancel, giving you this. And then here you end up with that. So we're just going to flip the whole thing and change the direction of the inequalities. So we get n minus 1 s squared all over 4.575 is greater than sigma squared greater than n minus 1 s squared all over 19.675. Right? And then we're going to change the direction. We're going to write the smallest number first, then the middle number, then the largest number. So I'm just going to change the directions. N minus 1 s squared all over 19.675 is less than sigma squared less than n minus 1 s squared all over 4.575. And then finally, all we have to do is take the square root of all three parts of the inequality. And that gets us my equation. So that's going to be n minus 1 s squared all over 19.675 square root of that, less than sigma, less than n minus 1 s squared all over 4.575 square root of that. So it's exactly what I did a minute ago, except I replaced early on the chi squared with this number. Leaving things with chi squared seems to make people very confused. So it's just a number that we get from the table. So it's just some constant value we get from the table once we find the value of the degrees of freedom and the confidence interval that we want to find. Yeah.
So on the test, can we just jump from the top?
Oh yeah. So like this part right here is not something that you're expected to repeat whenever you do your homework or when you do the test. Let me show you what you do. Okay. So what I would expect. So this part here is not part of what I would expect you to write down. I would expect you to start from here. This is the formula that's in the back of the book. You can just start right there and say that it's n minus 1 times s squared over chi squared. Now, even though it's the left one, I know it's going to be the right one because of the flipping of the inequalities. Less than sigma, less than n minus 1 s squared over chi squared left, and it's the square root of all of those. And now we just plug stuff in. I know that this is the right value, which is the big number, 19.6. Yeah, that's the one that ends up being there. So we end up with 12 minus 1 times s, which is equal to 0.3492 squared all over the big chi squared right, 675. And then we're going to take the square root of that whole thing. Another common mistake is that this is called the chi squared value. So when I do it in general, like we did over here, we end up with a formula for chi squared. This guy. Okay, this does not mean that you have to square that. It doesn't work that way. this chi-squared is already kind of like part of the title. Okay, it's already built into here. Every number in here is a chi-squared value, so you do not have to square this denominator. Okay, good. Question?
So you care if it's like that direction,
Well, this is the way the book is this is the way the formula is given to you, with the lowest number first on the confidence interval and the biggest one over there. So you just got to make sure you figure out which is which. But I mean, also when you do this, if you automatically know which number is smaller, it goes on the left. So it should be pretty easy to note when you make a mistake. So this will be 12 minus 1, 0.3492 squared, all over the smaller of the chi-squareds, 4.575, square root of that whole thing. So now let's figure out what these are. I end up with 0.02611.
Yes.
0.2611 on the lower bound, sigma, and then the upper bound, 0.5415, and this guy is 0.5415. So there's an interval. Okay. Again, the interpretation is, if 100 people go out there and find their own samples, each of them will have their own sample standard deviation. And so when they go through this process right here, they'll come up with their own confidence interval. And I expect that 90 out of those 100 different intervals will contain the true standard deviation of the population, and 10 out of those 100 intervals will fail to include the true standard deviation of the population, and we never know which is which.